Hi again. So we have reached the course about sorting and heap. So we'll start with the heap part, and in the second recording I will be posting the lecture about the sorting algorithm. So before starting with the heap, we will just recall priority queues and what's priority queue, and what we have already done in this course, and why we will use it and implement priority queue using heaps. So a priority queue is a data structure. So as we have seen, so it's like a queue. So we can add from the front. So this is the front and this is the rear. So we can either add from the front or on the rear, or delete from the front or from the rear. So mostly priority queue, it allows to insert and to delete the minimum and delete the maximum, because it depends on how we are inserting in priority queue. So in priority queue, the elements are sorted according to a priority. So it depends sometimes if the priority, so the smallest priority is the most highest priority, so we'll place it on the front, and those with those priorities would be on the rear. So we can either delete the maximum or we can delete the minimum. So this is the DQ operation. So we call a priority queue an ascending priority or a descending priority. It depends on how we are inserting the elements into this queue. So in our course, we have implemented a priority queue dynamically and statically using a static array. However, the implementation was the complexity of the algorithms were in n square. So, however, a priority queue can be implemented using heaps with more lower complexity around n log n. So we'll see that. So the main operations of a priority queue, so it's the insertion of a key and a data, the deleting the minimum or the maximum, depends, it's the rear or front, depends on how we are inserting the elements into the priority queue, and to get the minimum and the maximum, so the front or and the rear element. So we have here different names, however the functionalities are the same as a queue, as we have already done. So as for the auxiliary operations for the priority queue, so we can find the case smallest, the case largest, the size of the priority queue, and most importantly for now is to do a heap sort using a priority queue or a heap. So as for the application, so we have already used the priority queue in Dijkstra and the minimum spanning tree in Prim's algorithm. So we can also use it in Huffman coding algorithm in data compression, and in, for example, defining the case smallest element in an array. So for the implementation, we have a very long number of implementations. So first we have the unordered array implementation. So we have an array and we place the elements in an unordered fashion. So the insertion would cost just one operation. So we add the element at the end of the array. However, for deleting the minimum, for example, it will cost us an operation because we need to check all the elements in the array. So we can the same use an unordered linked list. So here again, the insertion is it costs just one operation. However, the deletion of the minimum will cost an operation. So we didn't implement these two. We have implemented the ordered array implementation and the using a queue in our example. So and we implemented the ordered list implementation. So they are both the same, and in both cases the insertion would cost us n because we need to insert in ordered fashion. However, for deletion, it will cost us just one operation. As for the other implementation, so we have either binary search tree or balanced binary search tree or binary heap. So for the binary search tree, so on average we have the deletion and insertion, it takes log n times, and for the worst case for the balanced binary search tree is again log n time. However, for the log n, all the operations are on log n, and one operation would cost us to find the maximum and minimum. So here is a comparison between all the implementations. So as you can see, the most advantageous one are the one that uses trees, and so here is one. So on the most economical one is using binary heaps or a heap. So let's move now to the part concerning heap. So a heap is a tree and it has some special properties. So as in the BST, so the heap, we know that it's either, we'll see it in a while, either as a minimum heap or a maximum heap. So a heap, when we have an element, so the elements that below the root element, so they are either greater than the root element or less or equal than the root element, and so on. So again, in this level, in this subtree, we have the root 2, so either all the lower element, all its children, and are less or greater than 2. So again, the heap, so all the elements should be at a level h or h minus 1. So it means that, let me erase. So it means that I need to fill the element level by level. So I can allow, for example, to have one element. However, for example, this one is correct. However, if I do that, this is not a heap, because it should be filled level by level. So we can say that a heap is a complete binary tree. So let's see an example. So here we have an example. So on the tree or the heap on the left is a heap, because we have here 7 and all the elements here are less than 7. Again, we have 3 here and all the elements here 1 and 2 are less than 3, and the same for here. However, here for 11, so all the elements, so we have below the 11, so we have elements that are less than 11 and we have elements that are greater than 11, and so this is not a correct heap. So we have two types of heap, either a minimum heap or a maximum heap. Whenever we say it's a minimum heap, it means that if the root is a number, so all the elements that beneath this number are greater than him. So the minimum is on the top. As for the maximum heap, it means that the root is maximum and all the elements below him are less than the root. And again, recursively, so all the elements, for example, here 13 should be less than 13, and so on. So to represent a binary heap, so you can represent it as a tree. So it's not recommended because it will be very difficult. However, we'll represent it using an array. So the elements of the tree, so we can see it here. So we will number the element of the tree from 0 and level by level. So this is the numbering. So we will find the element 17 at index number 0, the element 13 at index number 1, and the element 6 at index number 2, and so on. So in the remaining of this part, so we will just talk about a maximum heap. So, and the same applies for the minimum heap. And then we will just discover some relationship between the indices and, for example, parents, left child, right child, in order to manipulate the heap like a tree. However, we'll be manipulating arrays. So to define a heap, so we need an array. So this is the dynamically allocated array. We have the capacity, so this is the maximum capacity of the heap. For example, it can contain 20 elements. However, when we have a limited number of elements, so we'll have a count. So count is the currently number of elements in the heap, and the heap type, it's either minimum or maximum, so just 1 or 2 depends on the type of the heap. So to create a heap, so I need to so I have the capacity, this is the maximum capacity, and the type of the heap. So I need to allocate the heap structure because it's a pointer, and we need to fill these elements. So the count, the capacity, and the heap type. So the heap type, it's already passed by parameter. The count, the currently number of elements in the heap, is equal to 0, and the capacity is passed by parameter. As for the array, so we need to allocate a capacity elements of size int, and then we return the heap. So the time complexity is 1 because we don't have here any loops. So we have some properties in this heap. So for example, I can find the parent of a node. For example, if I have here 4, so we know 4 that it's at index 4. I need to find the parent, which is at index 13. So how can I find that? I have the index, which is 4. I do 4 minus 1 over 2. So 3 over 2, and we know that we have here a division of integers, so the answer would be equal 1. So the parent of 4, we can find the parent of 4 at index 1. So you can try all this stuff, so or you can use this function. So if I want to find the parent of the index I just need to return the index of I minus 1 over 2. So the same if I want to find the left child or the right child. So if I have 13 here, so 13 is at index 1, so I need to find one and 4, so which are they are at index 3 and 4. So what can I do? So to find the left child, I multiply 2 multiple I plus 1. So 2 multiple 1 plus 1, it's equal to 3. To find the right child, I do 2 multiple I plus 2. And again, all these complexities are in 1. So why we need those functions? Because later on we need to rectify a tree in order to verify a heap. So for example, if I have 17, 4, 1 and 13, so this is not a heap because I have here 4, it's not a max heap, so I need to move 13 up. So in order to move it up, I need to find the parent of 13 and so on. So we will check these in a while. So to get the maximum element of a heap, so the maximum is obviously here, so it's at index 0, so I just need to return the H array of 0, and again the complexity is equal to 1. So here we have the heapifying of an element. So obviously this tree is not a heap because 1 is misplaced. So I need to change the placement of 1 in order to have a heap. So what can I do? I don't have many choices, so I cannot get it up because it's a max heap. So obviously I will move it down. So if I need to move it down, I need to place another element in place of 1. So what can I place? If I place 5, I will have this. If I place 5 and place 1 here, I will have the same problem because then I will have 10, 8 and 7. They are greater than 5. So obviously I need to pick the maximum between of the children. So we will use the two functions, left child and right child. So we will pick the maximum. So we will get 10 here and 1, and again we will do that. So this operation is called heapifying. So we take an element and we will try to push it down into the tree in order to verify the heap property. So this is the observation. So what we will do, so we need to find the maximum of its children and swap with it. So we will find 10, we will swap. So for now it's not a heap also, so because 1 is misplaced, and I need to find the maximum which is equal to 8, so I will swap, and now the tree is a heap. So this is, we call it a percolate down because we take an element and we move it down. So we will do this operation while we do what's called a heap sort while sorting the array. It's in the second recording. So to percolate down, so let's check the code. So I have the index of the element and I need to push it down. So for that I found the index of the left child and the right child, and then I need to find the maximum between these three elements. So this is here the calculation. So I'll calculate if the index of L, so the left child, is greater than I. So if the element that I need to swap, so if the left child is maximum, I'll save the maximum here. Otherwise I will check the right one. So if the right one is greater than max, I will save the right one, and in the both cases, so here we have the else, we keep I as maximum and everything else. So if maximum is different than I, so if there's a maximum beneath me, so I need to swap. So here we are swapping both elements, and then what you do, I need to percolate again from the newly modified element. So if we go back, so whenever I do that, I need again to launch to call the function from this element. So it's recursive and it takes at maximum log n time because we are just moving an element into one branch, so it's log n the complexity. So this is for heapifying. So for deleting an element in the heap, so usually we cannot delete an element from anywhere from the heap, so usually we just delete the root, and in order so we delete the root and we need to place another element. So what we will do is that we will pick the last element, we will place it on top, and then we will percolate it down. So this is the idea. So while deleting the element, so we can delete just the array of 0, so it's the root element, so we keep it data and then we will return it, and we will bring the last element, so it's at array of count -1, we will place it on top of the heap, and then we will percolate it down. So we don't have an element example here, so let me do that. So this is the heap, so I need to delete 31. In order to delete 31, I will delete it. I will place 7 here. So I will remove that and place 7 here. So now the tree is not a heap, so I need to do the percolation, all the stuff. So I need to get down 7. So I'll find the maximum between these two. So obviously 21 is greater than 10 and greater than 7. I will swap. So now I will call percolate down from index containing 7. So again, I will find that the maximum is equal to 18. So I will switch those two, and now I have the heap, which is a maximum heap, and it's a correct heap. So this is for the deletion, and we cannot we can delete just the top element, which is the maximum in the tree in the heap. So we will use that also in while doing the heap sort, because we have always the maximum, so we can always pick the maximum. So again, so once we do that, and we do the percolation, so we will end up with the second maximum here, and so on. We repeat that until there is no more elements in the heap, and so we will have at the end a sorted array. So we will see that in a while. So to insert an element into a heap, so this is the reverse operation. So we place, as I have told you, so we need to fill the elements level by level. So I will fill it in the last level when I have some empty spaces, and then I need to percolate up. So I need to move up the element. So let's see an example. So I have inserted here 19. So I will look. So I find here there's an empty space. So I have filled it with 19. So 19 is not in its place, so I need to percolate it up. So I will compare it with its parent. So 19 is greater than 14. Obviously, I need to swap. 19 is greater than 16. Again, a swap. And 19 is not greater than 31. So it ends here. So when inserting an element, so again, so I will add it at the end, and then I will move up into one branch. So again, it's log and the complexity. So to insert, so obviously I need, so let's keep this just for a while. So we need to increment the number of elements in the heap, and then I will start from count -1, obviously, because the array starts from 0, and I need to check the parent. So the parent is of index I-1. So if the data that I want to add is greater than its parent, so I need to move the parent to the index of the child. So for that, this is the element of the parent, the content. I will place it at the end of the elements, and then I will move up to the index of the parent. So in this operation, so it means that, let me erase. So I have here the index. So I find the parent, which is index I-1/2. If, for example, here 19 is greater than 14, I would place 14 here, and I will keep 19 with me. And then I have the 16. Okay, I will get it down, and here I will place the 19 and 16. So if you can see, every time I'm jumping I-1/2, and this is here. So obviously the counter is moving up I-1/2, and at the end I would place the element data at index I. So whenever the count is equal to the capacity, so for example, if the heap contains 20 elements and I already have 20 elements and I need to add one more element, so I can resize the heap. So what does it mean, resize a heap? So I can allocate a bigger array, because I have done a dynamic allocation of the array. So the resize hit, I will create a new pointer to a new array. I would allocate this array, and I will double the capacity. So look, well, I have two multiple capacity, and then I will copy the old array into the new array, and then free the old one, and I will multiply the capacity by 2 in the heap. So this is an idea on how to dynamically work with arrays, and whenever you need more elements, you can recopy the content of the elements and have a bigger number of elements in the heap. So to destroy a heap, I just need to destroy the array, which is the pointer, and then I will free the heap, and I will return. So I place h in equal to null, and that's it. So to heapify the array, so we have an element, and I need to place it into a heap. So this can be done into n successive inserts. So we at each iteration I will insert one element, so it will take n log n in worst case, and we will see another version where we can create a heap from the array using just n operations. So we have an observation here that whenever we have, so we'll see it in a while. So if I have, this is the array, so you can see it's not a heap because I have placed the elements one by one. So the array is equal to 1, 5, 1, 2, 1, 2, 1, 3, 1, 8, 7, and 1. So this is the array, and I have considered it as a heap. However, it's not a heap, so I need to work with that. So if you can look well, all the leaf elements, they are already a heap because there is nothing beneath them. There's nothing to compare with them. So in order to work and to rectify this heap, I need to work with the first non-leaf node. And we know that the first non-leaf node is at position I minus 2 over 2 or count minus 1 over 2. So we will start from here. And from here, we will do the percolate down. So for each element which is not heap, I will do the percolate down if it's not on its place. So let's do it here, because let me erase all. So we'll start from 2. So 2, I will look into its children. So 2 is maximum, so it's okay, it's in its place. 1, let's move here. So 1, it's not in its place because I have a maximum element beneath them, so I will pick the maximum. So I'll place 8 here and 1 here. And then I will move to 2. So 2 again is not in its place. I will move it with the maximum. So 2 here and 3 here. I will move here. So 1 is not the maximum. I will swap. And I will continue. So 1 is the maximum. There's no problem here. Then I have 5. Obviously, I would place 5 here, 8 here, and 5. So again, 5 is not in its place. So 7 here and 5 here. And then at the end, I have 1. 1 is not in its place. I'll place 1 here, 8. So again, 7 here and 1. Again, 5 and 1. So at the end, we will have this 3, 8, 7, 2, 1, 1, 1, 3, 5, 2, 1, 1, 1. And yes, this is a heap. So again, in order, whenever we have an array, so later on we will do that whenever we are doing the sorting stuff. So we will, one method is to consider, so this is the method 2, is to consider the array as a heap, and then I will rectify it by doing percolate down from the first non-leaf node. The other method is to insert each element at a time into the heap. So first I will insert 1, then I will insert 2, then I will insert 7, and whenever we are inserting, so let me do it. Let's erase. So again, the arrays are like the elements are like that. So first I will insert 1 into the heap. So this is the heap, and then I will insert 5. So obviously this is not a heap. I need to percolate up. It will become like this. So we have this, and then I have 1. So this is a heap, and then I have 2. So 2. So I'm filling level by level. So 2 is not a heap. Let's percolate up, and now it's a heap. Then I have 1. It's okay, it's good. And then I have 2. So 2, I place it here. It's not a heap. I will percolate up, and it's okay. And then I have 1. Good. Then I have 3. So 3, I need to move it 2 times up. So we'll end up, let's write it here, 5, 3, 2, 1, 1. We'll have here 2, 1, and 1, if I'm not mistaken. So, and then I have 1. Then we have 8. So 8 should be go up. So we move 8 to 1, 1 to, so we have here 1, 3, 5, and then 8, and then we will have 7. So 7 will go up. We'll have here 3, 5, 7, and then we have 1, and this is it. So this is the construction of the heap, one element at a time. And you can see, if you can notice, that this tree is different than the other tree. This is not wrong, however, it verifies the heap property. So to heapify an array, so we can either consider the array as it is and then do the percolation up. This is the second method here. So we have the array, so we consider it as a heap. So for that we are placing each element directly in the array. So it's the same, we are copying the elements and we are doing percolate down from the first non-leaf node and up to 0. And the complexity here is n. Look well. The first method that we have done, that we are inserting each element into the heap, it cost n log n. So, and this is it for this part, and see you in the next recording.